So if we ignore this constant term for now, because it's just basically adding like a DC offset to the overall plot, so we want now to examine the structure of this controller, okay, in the frequency domain and the log scale. Okay, so if we take this term, the term which contains the 0, so it's log the magnitude of 1 plus j omega over z. Okay, so in order to plot the frequency response of this, this is the magnitude term of this part. So in order to plot it, we can try to look at the extreme cases. Okay, so if this is our plot, okay, this is the 0 dB part, and the first, okay, we have our 0 here, okay, or the z, when omega equals z, so this is omega, and here we are this is the 20 log magnitude of 1 plus j omega over z. Okay, so we have two parts. Okay, so first of all, there is a region where omega is much less than z, and there is a region where omega is much bigger than z. Okay, so when omega is much less than z, we can basically ignore this term and becomes 20 log 1, which is 0, so we can say that we are almost starting at 0. But what happens when omega is greater than z? When omega is greater than z, so this becomes the dominant term and this becomes neglected, so we will have something like this. So it's 20 log magnitude of omega over z, and this implies that we are talking about something which is increasing by 20 dB per decade. Okay, so every multiplication by 10 you increase by 20 dB. So after the 0 you'll be going like this, before the 0 you'll be something like this. Of course, this is an approximate plot, okay, so the actual plot will be somewhere like this, but for now we can go with this one. Okay, so it's okay to use some approximations. You know, as engineers we like to do approximations because it makes things easier. All right, what about the other term? So the other term is essentially, it's minus 20 log 1 plus j omega over p. Okay, so it is gonna be very similar to this one, but the only difference is it's just gonna be the mirror of this figure. So it's instead of, so before the pole it's still at 0. Before, when omega is much less than p is at 0, when omega is greater than p, you're gonna be decreasing by minus, or going by minus 20 dB per decade. Okay, so we will gonna have something like looks like this. All right, and if you put those together, and this is where things become interesting, because if you just add those two together, what you will get is, you will get something like this. So at the 0, this is our 0, so it starts to increase until it reaches the pole, and then after the pole, okay, you'll find that the pole is going down by 20 dB per decade and the 0 is going up by 20 dB per decade, so they cancel each other out, so the magnitude becomes something like this. Okay, so this is the magnitude plot of our controller. This is assuming that the 0 is smaller than the pole, which is the case for the lead compensator. Okay, so now we go to the phase part. All right, so the phase is the same. So if we want to obtain the phase of this term, which is 1 plus j omega over z, so we're going to have something similar. Analysis. So when omega is much less than z, what will happen? Okay, for omega much less than z, you will have a phase of 0, right? Because it's just this term will be neglected and you have just have the one term. Okay, and when omega is much greater than z, so omega over z becomes very large and it goes to infinity, so the phase is 90 degrees. And when omega equals z, the phase will be 45 degrees. So this is quite easy. So when we plot the phase plot here for this term, so you have this 0 degrees here, and this is our 0, okay? So before the 0, it's 0. After the 0, it's 90 degrees. And in between, you have something like this. Okay, so it's 0 from here, and it's 90 degrees here, and it's 45 degrees exactly at the 0. So exactly at the 0 location, the phase is 45 degrees. And similarly, I'm not going to do this again, but similarly, it's easy to look at the other part. So the pole will introduce some delay, or phase lag. So you're going to have something like this. Okay? So this becomes negative 45 degrees, and this is negative 90 degrees, and these are the two terms. So this red one is coming from the 0, this other one is coming from the pole, and the overall response of the two of them will essentially be something like this. So if this is our 0 degrees, and we will have phase that increases and then goes back again. So between the 0 and the pole, the phase is going to increase. Okay, and it's no surprise then that this is now called a phase lead compensator, and the term phase lead is coming from the fact that phase is actually increased. So we are adding phase to our Bode plot, and we will see right now we will see quite shortly how this phase increase is actually quite useful in the control design. So we can use it to, for example, increase the phase margin of our system. All right. Okay, so the next part we will discuss how then can we